Dear students, welcome to EPG Pathshala. In today's module, we are going to discuss on the principle and applications of wind power generation. Wind is the air in motion. It is an indirect form of solar energy. By the solar energy or the kinetic energy is converted to the mechanical energy or the electrical energy in the form of the wind energy harnessing. India is one of the topmost country in the world by means of the wind energy harnessing and installation. We are rich in onshore and offshore wind energy potential. In this module, we are going to discuss on the energy available in the wind, what is the basics for the wind energy conversion, what are the parameters we should consider while designing the rotor, what is the principle behind the power generation from wind by the wind turbine. We will see the Beck's theory of theoretical maximum, the wind energy extracted using this wind turbine. We will see the applications as well as some limitations of this wind energy conversion system. Also the wind energy scenario in India. So the wind power is one of the indirect solar energy technology. The wind is the air in motion resulting from the pressure gradient caused by solar radiation. About 2% of the solar radiation reaching the Earth's surface is converted to kinetic energy, and this is sufficient to meet the energy demand if we are able to harness it. The kinetic energy of the wind is utilized directly or can be converted. The factors affecting the wind generation of an area are nature of the terrain, degree of cloud cover and angle of the sun. Various factors that affect the distribution of wind energy are mountain chain channelizes the air currents, hills, trees and building which act as obstructions and change the direction of airflow, frictional effect of the surface that determines the wind speed. This is the reason why wind speed is quite high at the seashore, as this frictional effect is less on the smooth surface. The climatic disturbances that results from rain that will affecting the wind speed. Topography of an area, for example, wind can speed up when passing through narrow gaps such as the mountain gaps. Coming to the energy available in the wind. The windmill or the wind system works on the principle of converting kinetic energy of the wind into mechanical energy. So we should know what is the energy available in the wind. As we all know, power is equal to energy per unit time, and the available energy can be equated to the kinetic energy of the wind. So kinetic energy of any particle is equal to half mv square, where m is the mass and v is the velocity. Now the amount of air passing in unit time through an area A with velocity v can be calculated by multiplying the area with this velocity. Its mass is equal to its volume, which is multiplied by density rho of the air. That is, density is equal to mass by volume. By applying that equation, we can equate the mass is equal to rho AV, where m is the mass of the air transversing the area A swept by the rotating blades of a windmill type generator. Substituting this value of m in kinetic energy equation, we will get half rho A V into V square, which can be equated or which can be that is equal to half rho A V cube watts. And the wind power available is proportional to air density. So it is equal to 1.225 kilogram per cubic meter at the sea level, and the variation in this air density over the year is around 10 to 15%. This may be or this is because of the changes in pressure and temperature. It's also, the wind power is also proportional to the intercept area we have seen from the equation. So an aeroturbine with large swept area has higher power than that with smaller area. Since the area is normally circular of diameter d in horizontal axis aeroturbines, A can be equated as pi d squared by 4. Substituting this equation in 1 by 2 rho AV cube, we will get the available wind power is equal to 1 by 8 rho pi d square V cube. Wind energy conversion system. The air circulation results from non-uniform heating of Earth's surface by the sun. The expansion of air occurs immediately above a warm area which is forced upwards by cool, denser air which flows in from the adjacent area. The energy in wind is due to this motion, and the energy is harnessed by wind turbine which is mounted on a tower, and the speed of the wind depends directly with this height. The tower height equal or more than 30 meters is beneficial as it can be used faster and less turbulent wind. The wind speed at a height of 10 meter is 20 to 25% higher than the surface and 30 to 60% at a height of 60 meter. So, the optimum or the best height for the tower is more than 30 meters if you need to harness more energy. This is due to reduction in drag effect of the Earth's surface. The average wind speeds in a particular location need to be exceeded at least 6 to 8 meter per second for a small wind turbine to be economically viable. That means the optimum wind speed is, it should be greater than 6 or it is 8 meter per second. The wind energy conversion system, it is also known as the aerogenerators or wind turbine generators or simply the wind turbines. Let's see what is the basic for the wind energy conversion. The basics are lift and drag forces. The extraction of power from the wind depends on creating certain forces and applying them to rotate a mechanism. There are two primary mechanisms for producing forces from the wind: lift force and drag force. The lift force acts perpendicular to the airflow while drag force acts in the direction of the flow. Lift force, that is the component of total force, that is pressure force and shear force on the body in the direction perpendicular to airflow, and it is known as the lift force. This force tries to lift the body. It is given by the following equation: delta FL is equal to CL, which is the lift coefficient, multiplied by 1 by 2 rho nu1 square A. Drag force. When a body or the aerofoil is placed in uniform airflow, there are two forces acting on the body, which are pressure force acting normally to the surface of the body and shear force that can be resolved in the selection parallel to airflow. It is known as the drag force. It always opposes the relative motion between the body and the air, and it is given by the equation delta FD is equal to CD, which is drag coefficient, and A is the projected area. So, the delta FD is equal to CD multiplied by 1 by 2 rho nu1 square A. These forces are produced by changing the velocity of the airstream flowing over either side of the lifting surface. Speeding up the airflow causes the pressure to drop, while slowing the airstream down leads to increase in pressure. The change in velocity leads to pressure difference across the lifting surface. This pressure difference produces a force that begins to act on high pressure side and moves towards the low pressure side of the lifting surface, that is known as the aerofoil. Now, from these two forces, the lift force is good for the energy harness, wind energy harnessing. So, what are the mechanisms for producing this lift? A good airfoil has a high lift drag ratio. The lift increases as the angle formed at the junction of airfoil and the airstream becomes less acute up to the point where angle of the airflow on the low pressure side becomes excessive. Due to turbulences, the lift decreases and drag force increases substantially, and that is known as stalling. For efficient functioning of the wind turbine, there should be high lift but less drag force. Apart from this airfoil, the two other mechanisms for producing lift are Magnus effect and Thwaites slot. Magnus effect is caused by spinning a cylinder in an airstream at a high temperature. The spinning slows down the The spinning slows down the airspeed on the side where the cylinder is moving into wind and increases it on the other side. The air is blown through narrow slots in a cylinder and it emerges tangentially, and that is known as the Thwaite slot. This creates rotation of airflow, which in turn generates lift. So these are the mechanisms which helps in production of lift force. Coming to the different terminologies related to wind turbine before seeing the principle behind it. Swept area. This is the area perpendicular to wind direction that a rotor will describe during one complete rotation, or the area of imaginary circle which is formed during the rotation of wind turbine. There are different wind velocities. Wind velocity is the velocity of free air stream at sufficient distance away from wind turbine where there is no disturbance due to rotation of the wind turbine. Incident wind velocity is the velocity at which wind strikes the blade, and this velocity is always slightly lower than the free airstream velocity, which is nu0, and incident wind velocity is nu1. Blade linear velocity. It is the velocity of the blade due to the rotation of the blade. If omega is the angular velocity of the blade and r is the length of the blade, then blade linear velocity is equal to omega multiplied by r. Relative velocity. It is the relative velocity of wind with respect to the moving blade. It is a vector sum of incident wind velocity nu1 and blade linear velocity. The mathematical representation is given here. The specified wind speed at which a wind turbine's rated power is achieved is known as the rated wind speed. Survival wind speed or extreme wind speed is the maximum wind speed that a wind turbine is designed to withstand. You can see different velocities in this picture. Now the angle of attack or angle of incidence, which is denoted by alpha, it is the angle between the center line of the aerofoil, that is the blade cross section, and the relative velocity nu r. The airflow remain attached to the aerofoil for a small angle of attack. The airflow is separated from the aerofoil for the large angle of attack. Now the pitch angle or blade setting angle, which is denoted by gamma. It is the angle between the center line of the aerofoil and the direction of linear motion of the blade. The output of a turbine is greatly influenced by blade pitch angle. The blade pitch control is a very effective way to control the output power, speed or torque of the turbine. We have already seen the lift force and the drag force. There are other forces also like axial force. The total force, that is the pressure force and shear force, can also be resolved along the axis of rotation of blade and perpendicular to it. The component of total force acting on the blade along the axis of rotation of the blade is called the axial force. The axial force does not contribute to the rotation of the blade. It is also called the thrust force and has to be balanced by a suitable reaction force generated by any thrust bearing provided on a rotor. The axial force contributes to waste energy. It is represented as delta Fa, which is equal to delta Fl cos phi plus sin phi, and here this angle phi is equal to alpha plus gamma. And the tangential force, it is the component of total force on the blade acting tangential to its circular path of rotation. This is the force which contributes mainly to the useful energy extracted from the wind energy, and it should be as high as possible, and is given by the equation delta Ft is equal to delta Fl sin phi plus delta Fd cos phi. Now we will see the principle of power generation from wind in a wind turbine. The energy can be extracted by partially decelerating and expanding the airstream, that is the reduction of pressure using wind turbine. You can see the airstream in this figure. The rotor of the wind turbine collected the wind from the all areas swept by the rotor. The area swept can be considered as airstream tube, which is continuously expanding air. This airstream model is also known as the Betz model of expanding air. As the air mass flow rate should be the same, it must decrease within the stream tube according to the law of continuity. The wind speed must decrease as air expands. As shown in this figure, airstream tube has area of A0 at upstream area of, as shown in the figure, airstream tube has area of A0 at upstream, area of A1 while passing through rotor blade, that is aerofoil, and area A2 at the downstream. So considering that nu0 and nu2 are the wind velocities at upstream and downstream, the velocity reduction from nu0 to nu2 means that there is reduction in momentum of wind as it passes through wind turbine, resulting in a force being exerted on the blade of rotor, and it is given by the equation force F is equal to m into nu0 minus m into nu2, which can be written as F is equal to m into nu0 minus nu2, where m is the mass flow per unit time through the stream tube. The above force is exerted at a uniform rate when airflow moves over the rotor blade with velocity of nu1. Therefore, power extracted is equal to the work done by airstream in moving for a distance of nu1 against force of F, and it can be given by power of turbine Pt is equal to F into nu1. Now substitute the F value, that is m into nu0 minus nu2, in this equation number 9. We will get Pt is equal to m into nu0 minus nu2 into nu1. The power extracted by the wind turbine from the wind is equal to the change or loss of kinetic energy of the wind. So the delta Ke is equal to Pw, which is equal to 1 by 2 or the half of the m nu0 square minus nu2 square. The energy extracted equal to energy lost by wind. So the extracted is Pt and the lost is Pw. So we equate these two values of these two, Pt and Pw, we will get m into nu0 minus nu2 multiplied by nu1 is equal to half into m into nu0 square minus nu2 square. Nu1 is equal to, from this we can calculate nu1 is equal to nu0 plus nu2 by 2, where nu1 is the average of the nu0 and nu2. So substituting this value in Pt, we will get Pt is equal to m into nu0 minus nu2 multiplied by nu0 plus nu2 by 2. So that is half of m into nu0 square minus nu2 square. So the mass flow m is the product of area, velocity and density, and m can be represented as A1 into nu1 into rho, or the value of nu1 which we have already calculated. If we substitute that one, we will get m is equal to A1 into nu0 plus nu2 by 2 into rho. Now substitute the Pt value and Pt value of half m nu0 square minus nu2 square, and the A1 value of A into, and substitute the m value, that is A1 into nu0 plus nu2 by 2 into rho, we will get Pt is equal to 1 by 4 into A1 into rho into nu0 square minus nu2 square, which is multiplied by nu0 plus nu2. Let's imagine or assume, let's assume there is an interference factor alpha is present, then nu1 is equal to 1 minus alpha into nu0. Alpha is equal to, then alpha is equal to 1 minus nu1 by nu0, which is equal to 1 minus nu0 plus nu2 by 2 into 1 minus nu0 plus nu2 by 2 by nu0. So, nu 2 is equal to, so the alpha is equal to nu 0 by nu 2 by 2 multiplied by nu 0. Nu 2 is equal to 1 minus 2 alpha into nu 0. Now, if this is the case, then the turbine power is, or the alpha is there, or the interference factor is present, then the turbine power is equal to Pt, which is equal to 1 by 4 A1 into rho into 2 into alpha into nu 0 multiplied by nu 0 plus 1 minus 2 alpha nu 0 all square, which is equal to 4 into alpha into 1 by 1 minus alpha all square multiplied by 1 by 2 rho A1 nu 0 cube. And the wind power is given by Pw is equal to the 1 by 2 rho A1 nu 0 cube. Substituting m, we will get A1 multiplied by nu 0 plus nu 2 by 2 into rho. From these equations, we have Pt is equal to 4 into alpha multiplied by 1 minus alpha square multiplied by Pw. And this value 4 into alpha multiplied by 1 minus alpha square is represented as Cp, which is the power coefficient. It is represented as this value 4 alpha 1 minus alpha all square. So, the Pt is equal to Cp, that is power coefficient multiplied by the Pw. The power coefficient Cp, it indicates the portion or fraction of wind power that is extracted by wind turbine. The ideal or maximum theoretical efficiency, that is eta max of a wind turbine, is also known as the power coefficient. It is the ratio of maximum power obtained from the wind to the total power available in the wind. So, you can say it is a ratio of actual power to the theoretical power. And the power coefficient is equal to, you can calculate it by the power output from wind machine divided by the power available in the wind. So, that is P actual divided by P theoretical. When alpha is equal to 0, then nu 1 is equal to nu 0, nu 2 is equal to nu 0, and there is no power generation takes place. That means, if there is no interference or the alpha value is 0, then there is no power generation. When the alpha is 1 by 3, then nu 1 is equal to 2 by 3 nu 0, 2 by 3 nu 0, and nu 2 is equal to 1 by 3 nu 0, and the maximum power generation takes place. When the alpha is 1 by 2, then nu 1 is equal to 1 by 2 nu 0, nu 2 is equal to 0, and only turbulence occurs at the downstream. When alpha is equal to 1, then nu 1, and it results in the stalling of the turbine. That means, when alpha is equal to 1, stalling occurs. Let us see what is the theoretical maximum wind power from the available. The air density, let us see the theoretical maximum wind power that can be produced by the wind turbine. The air density is proportional to the air temperature and the air pressure, both of which vary with height above sea level. The power in the wind cannot be completely converted to mechanical energy of a wind turbine. The losses due to friction reduce the actual wind power. The theoretical maximum of energy extraction from wind was calculated by Betts in 1926, and this theory is known as the Betts theory. The power output from wind turbine is given as Pt is equal to 1 by 4 A1 rho multiplied by nu 0 square minus nu 2 square into nu 0 plus nu 2. The power output depends on outlet velocity nu 2, hence for the maximum output dPt by d nu 2 is equal to 0. And so, nu 2 is equal to minus nu 1, which is impossible, and nu 2 is equal to nu 1 by 3. Substituting nu 2 is equal to nu 1 by 3 in this equation of Pt, we will get Pt is equal to 8 by 27 rho multiplied by A into nu 0 cube, which is equal to 16 by 27 multiplied by Pw, and which is 59.3% of the PW. As per Betts theory, so a wind turbine is able to utilize only 59% of the wind power even if no losses has occurred. And so, the power is multiplied by a factor of 0.59 to get the actual value. When some unavoidable soil losses occur, the turbine is able to utilize only 42% and the value of this reduced from 0.59 to 0.42. There are some parameters which should be considered while designing the rotor of wind turbine. One is solidity. It is the ratio of projected area of blades to the swept area. So, you can calculate solidity by dividing projected area of blades by the swept area. Let us do an example. A wind turbine has a rotor of 6 meter with 30 blades. Each blade has a width of 0.3 meter. What is the solidity? So, solidity is projected area of blades divided by swept area. So, 30 is the number of blades and the width is 0.3. So, multiply 30 multiplied by 0.3, we will get the projected area of blades, and the swept area is, you are having the rotor of 6 meter. So, pi r square, so pi into 6 square. So, applying this 30 into 0.3 by pi into 6 square, we will get 7.96%. So, that is the solidity. So, greater the solidity of a rotor, the slower it need to turn the intercept the wind. The slower it need to turn to intercept the wind. When wind wheel has a lesser number of blades, it need to rotate fast to intercept the wind, so that wind should not be lost through the large gap existing between two blades without imparting a part of wind power. So, solidity is important in designing the rotor. Another one is the tip speed ratio. It is denoted as lambda. The tip speed ratio is defined as a ratio of the speed of tip of the rotor blade to the speed of coming air. That is tip speed of the blade divided by wind speed, which is equal to omega multiplied by r by nu 0, where omega is the rotational speed of the rotor, normally expressed in radians per second, and r is the radius of the rotor in meter, nu 0 is the wind velocity in meter per second. So, the tip speed ratio is omega r divided by nu 0. For a particular wind speed, there exists an optimum turbine speed. For a particular wind speed, there exists an optimum turbine tip speed to produce the maximum output. It is very important to match the rotation of wind turbine to the corresponding wind speed. The rotor blades of a wind turbine interact with this wind. So, the slow rotation of the blades allow wind to pass freely through rotor swept area without interaction, while for the fast movement, rotor swept area act as barrier deflecting wind and cause turbulence, thereby losing the wind power. So, the windmill or the wind turbine or the wind blade which is rotating fast has tip speed ratio greater than, is having wind speed ratio greater than 1. 2 or 3 blade rotors rotate faster and have tip speed ratio of 3 to 10. More bladed rotors rotate slowly, having tip speed ratio between 1 and 2. So, the optimum one is having the 2 or 3 blade rotors. That is why we will see, or we are normally seeing, or the commonly used wind turbines are having 2 or 3 blades in order to get the more efficiency. The optimal tip speed ratio for horizontal axis, a 3 blade turbine which are predominantly used in the onshore and offshore wind farm is approximately 5:1 to 6:1. Let us calculate tip speed ratio. Find the tip speed ratio if a 6 meter diameter rotor has 6 meter rotor. Find the tip speed of a 6 meter rotor which has a rotation of 20 rpm and wind speed of 4 meters per second. So, tip speed ratio lambda is equal to omega into r by nu 0. Omega, that is radians per second. So, it is equal to pi r n by nu 0. Substituting that, we will get 1.6. So, that is the tip speed ratio. Now, what are the factors that influence the output from a wind energy converter? One of the important factor is the wind speed. We have seen that wind power is calculated as 1 by 8 rho pi d square v cube. So, it's if the wind speed is doubling, this wind power is increased 8 times. The maximum wind energy available is proportional to cube of the wind speed. So, a small increase in wind speed may increase the wind power. The cross section of wind swept area by the rotor is also influencing the output. The diameter of the intercept area, the maximum power available from the wind depends on square of the diameter of intercept area. If we double the diameter of the rotor, the available wind power will increase by 4 times. Another factor is the overall conversion efficiency of the rotor, transmission system and generator or the pump. The various components of the wind turbine affects the output. Almost all large wind turbines are of horizontal axis wind turbine designs which are having an upwind rotor with 3 blades which is attached to a nacelle on top of a tall tubular tower. So, the wind energy is captured by the rotor blades in the turbine and the kinetic energy is converted by the wind turbines to mechanical power. So, the conversion of kinetic energy into mechanical or electrical energy is given as Pmax is equal to m omega which is equal to m2 pi n, where m is torque, n is rotational number and omega is angular velocity. The mechanical power in the rotation of blade, the mechanical power in the rotor blade is coupled to a transmission or gearbox that is having the transmission or gearbox efficiency. So, it is given in this figure. The optimization of wind turbine designs to suit the different wind conditions and use of a variable pitch control system, yaw control, large size blades, variable speed drive, tilt control of blades, stall control by shifting of blades, eddy current braking system to maintain the speed, power electronics. This can also increase the efficiency of a wind turbine. Now, we will see the selection criteria for the wind turbine sites. There should be high annual mean wind speed. This is the basic requirement for a successful use of a wind farm or windmill which is having adequate supply of wind with good wind speeds, as wind power is proportional to the cubic power of wind speed. There should not be any obstruction. There should not be any high structure to obstruct wind for a distance of 3 km. Open plain, that is the site should be open plain such as open seashore line when the that windmill or the is located on hill or ridge with gentle slope. So, it should have an open plain, whether it is an onshore or offshore, it should be having an open plain without any obstruction. The height, the wind speed increases with height, so it can be obtained when the windmill is normally located on a hill or a ridge with gentle slope. So, we need not to spend on the tower, much on the tower. We need tower but not too high. Near lake or the ocean, it is one of the good criteria or one of the potential area for the wind turbine. So, the differential heating of water and land generates wind of sufficient speeds. So, we will be having the wind with optimum wind speed in those area. Another one is the topography. Normally, the mountain gap helps to channelize and speeds up the wind. So, the areas which are having such things should be encouraged. Favorable land coast, that is important for the cost of the project. Then it should be near to the load center. So, it reduces the cost of transmission. It should near to road or rail link which helps in the installation. And the availability of the data, wind data of the site will also help in designing that wind turbine. The benefits of wind energy. So, it is a potential energy source especially in the rural areas where electricity is not accessible. The energy production is high from a suitable wind turbine design. So, it is mainly we are using this for the electricity production. It has a low maintenance cost, it is clean fuel, pollution free, and it is eco-friendly fuel. It has applications like, there are two types of small scale wind turbines which are utilized in domestic, community and wind energy projects. The power generated by wind turbines are connected to grid. It can be state or central. So, the first windmill used for the production of electric power was built in Scotland in 1887 by the Professor James Blyth of Anderson's College. So, we have two types of this wind energy which is produced for the electricity usage. One is standalone system which are used for electricity production for battery charging. It is used for running small electrical appliances mainly in the remote areas with no power supply. It helps in the water heating or pumping, electric livestock fencing, lighting or any kind of small electronic system which is needed to control or monitor remote equipment. So, standalone systems mainly for the small things or small applications. Now, the another one is the grid connected small wind turbines. So, here the output from the wind turbine is directly connected to the existing mains electricity supply. So, grid connected. This type of system can be used both for individual wind turbines and for the wind farms which export the electricity to the electricity network. And the group of wind turbines which are located in the same place for electricity generation is known as wind farm, or it is also known as the wind power plant. It varies in its capacity of few megawatt to hundreds of megawatts. So, a large wind farm may consist of several hundred individual wind turbines distributed over an extended area, but the land between the turbine may be used. So, one advantage over this is this land between the turbine can also be used for the agriculture or other purposes. Though it has some other negative impacts like noise pollution as well as some other damage to the birds and biodiversity. The largest wind farm in this world is Gansu wind farm. So, the wind farm can be located onshore as well as offshore. But it has this wind energy has some limitation, especially these are erratic in nature, is unsteady and not reliable as it varies over the places at time. So, depending on wind are possible only in those areas which are having an optimum wind speed which is capable of running the turbine, otherwise it is not cost effective. Let us see what is the wind energy scenario in India. The world leader of wind energy is China, which is followed by US and Germany, and we are in the 4th position by the by the installation, wind energy installations till March 2017. We have already installed 31 gigawatt, and it accounts around 6.6% of the global market. The wind energy potential in India is estimated to be 2.5 into 10 to the power 4 megawatt. So, we are having a Center for Wind Energy Technology, that is CWET of MNRE, which is located in Chennai, which is responsible for the wind resource assessment in the country. That includes R&D, technology upgrading, testing, certification, standardization in close association with the wind turbine industry. The government has started wind energy demonstration programs with installations of wind pumps, wind battery chargers, standalone, wind electric generators and wind farms. So, the largest power rating in India is given to the wind energy generator of 2 megawatt capacity that is installed in Suzlon in Tamil Nadu, which is having the largest power rating in India. The maximum this wind energy generation installations are done in Tamil Nadu, which is having capacity of 1639 megawatt, while the maximum gross estimated wind potential is in the Gujarat, having 9675 megawatt. So, this map shows the wind resources in different states of India, and these are the major windy states in India. The main one is this is as per the installed capacity of the wind power. So, Tamil Nadu is having the highest, followed by the Maharashtra, Gujarat. Though I have told you that the potential is highest in the Gujarat. So, this table shows the wind potential states, thus they are providing some promotional tariff for the wind power projects. So, the major wind potential states, they are providing this tariff for these projects. So, to conclude, we have seen that wind is not constant over the different areas. It changes. So, the wind generated and distributed depends on different factors. And the energy available in the wind is calculated as 1 by 8 pi d squared v cube. So, this energy is directly proportional to the cube of the velocity and square of the diameter of the rotor or the windmill. So, if we increase the wind velocity by 2 times, the power is increased by 8 times. And we have seen that the optimum wind speed or the minimum wind speed, you can say, is for the wind turbine is it should be 6 to 8 meter per second and should be placed at a height of 30 meter and above. Then only the efficient harnessing of the wind power is possible. We have seen different terminologies associated with the wind turbines. The principle behind the wind energy generation from the wind turbine. And the Betts theory says that only the 59% of the total energy can be harnessed by the wind turbine if there is no other hindrances are present. We have seen different factors influencing the output of the wind energy from this wind energy conversion system. We have seen different applications of this wind energy by the standalone or by grid connected systems. We have seen the wind energy scenario in India, and we have seen that in India the Gujarat having the most potential, but the installation capacity is more in the Tamil Nadu. So, in India the onshore and offshore potential for harnessing the wind energy is very high, and we are having a potential of 2.5 10 to the power 4 megawatt of wind energy potential. Thank you.